All right, good afternoon. Today we have 2 lectures in one day so that you will have something to learn during the break. For this session, we want to cover chapter 11 in the text, and the principle is basically in the same manner as what we did for momentum transport. In momentum transport, when we set up the shell balance, we said that if the shape of the shell is not correct, you might end up with incorrect answer, or you might end up with something very, very complicated. So we want to somehow develop the equation so that we can use for any problems. Same thing would apply for shell of energy balance. Okay? In chapter 3, I show you how to develop equation of continuity, which is basically the equation for mass balance. Okay? During that time, we start using this mass equation, rate of mass going in subtracted by mass going out equal to accumulation of mass within the system. And the system in this case is basically a shell. Right? For the mass, there is no generation of mass. This is overall mass balance. Conservation of mass dictate that we do not have generation of mass. If we combine these two terms together, in minus out is basically what we gain. Just imagine you have money, you gain money, and you spend money at the same time. Whatever you have left as a net, this is what we call net flux or net rate of mass going in. And I emphasize on in here. So that means if these two terms, if you combine these two terms and the result is positive, that means you gain mass, or mass is going in. Mass going in should equal to whatever you have more, just like in your, if you're talking about money, whatever you gain is basically deposit into your pocket. So this is a rate of mass accumulated. Accumulation term, if it is positive, that means you have more mass accumulated in the system. If it is negative, then you have depletion of mass from the system. Okay? And during that, in chapter 3, the equation of this is basically d rho by dt equal to minus del dot rho v. And I'm not going through all this again. This was already derived in chapter 3 in momentum transport session. Okay? I just want to say that this part is a change with respect to time, so therefore corresponds to rate of accumulation. And this term is basically net rate of mass in. Okay? So you have to notice that whatever we emphasize on the word net rate of mass in, it is always related to minus del dot something. Okay? This something is whatever going into the system. So if we check the unit, okay, del is basically the differentiation with respect to x, y, and z, or differentiation with respect to position. So del is supposed to have unit of 1 over meter. Rho, which is kilogram per cubic meter, and V, which is meter per second. Okay, so if you look at this, you see that this meter and this meter cancel out. It's basically kilogram per cubic meter per second. So this equation was derived based on per unit volume of shell. Actually, this is mass balance per unit volume. Okay, so this is the rate of mass going in per unit volume. But whatever this equation would be, I would like to emphasize that minus del dot something represents net rate of something going into the system. All right? Now, we want to develop something in the same manner, but for energy. And this is equation for shell energy balance. For energy balance, basically you have flux of energy going in and out, and we have work done by external force. And this external force is basically gravity force. And you have to look at the sign. This is positive sign. That means this work is done to the system, is done on the system, so that the system gains some energy. So rate of work done by the system, done on the system by external force would be added to the balance. Okay? Same thing here, energy production, in a sense, it represents non-mechanical work like electricity applied to the system. Also, this one is positive. That means whatever it's come into the system will be count toward whatever you have in the pocket. And at steady state, it would be 0. But if it is not steady state, this term would be rate of energy accumulation. So that would be rate accumulation. Okay? This was used as an equation for our examples in chapter 10. Okay? Now, in and out term, if you combine in the same manner as we did earlier, this would be net rate of energy going in. So these two terms combined, if it is positive, that means you gain energy. Your system is gaining energy. And the gaining of energy here is by means of flux going in and out. Okay? So the flux for energy is E. This is combined flux. It is divided into conductive flux and convective flux. This is convective flux. And the work. This is flow work. We derived this part in chapter 9. Okay? When we, in chapter 9, before we gain this equation, basically, we start with this first. Before getting the enthalpy, we start with internal energy first, because we said energy is consisted of three forms: kinetic, energy, and kinetic, internal, and potential. Right? So this is internal energy. And somehow there will be pressure from this flow work. This equation was derived before getting the enthalpy. Okay? On the other word, you can split this enthalpy into internal energy and flow work term. And you get this part. Now, if we said that net rate of whatever going in is represented by minus del dot something. So that means net rate of energy going in is supposed to be represented by minus del dot the flux. Right? All these fluxes represent how energy will be transported into the system. Okay? And if you take fluxes going in subtracted by fluxes going out, you will end up with this form of equation, just like whatever we derive in mass. Of course, in details, you can start deriving from shell balance and reduce the size of shell in the same manner as what we did from mass balance, but it would be very complicated, so I figure that if I explain it like this, it would be easier to understand. All right, the key is net flux is represented by minus del dot that flux. So, if we start looking at these two terms combined into the net flux, I would get minus del dot E. Okay? And take E from the definition, that E is consisted of three fluxes: conduction, convection, and flow work. Okay? Take this into this equation. So basically, if you take del dot as a derivative or differentiation of the flux, I can expand this into minus del dot Q for the first term minus del dot the second term, which is convective transport okay. Remember, whatever inside this parenthesis is basically scalar. So it doesn't matter whether it's stay or not. You still have del dot this vector in the same manner as del dot Q. So the result here is basically scalar. And then the last part is minus del dot this flow work. Now this might be a little bit confusing. Tau is tensor. When you dot with vector, one dot reduce one direction. Tau has two directions. After dot products, the whole thing here turns to be vector, just one direction. And then you have vector dot with another vector, the whole thing here becomes scalar. All right? So the flux of energy is basically scalar. Now, from this, if I keep this del dot Q, but expand this term, this del dot in the convective term, split them into two terms. The first term is basically kinetic energy and internal energy. I keep velocity here. And then the second term, I take this to pressure. So I get minus del dot pressure V. Keep in mind pressure is scalar. Okay? If you can take this pressure to this velocity to another vector and then dot it by del later. And then the rest would be the same. All right? If we consider your unit, the unit of everything within this equation is supposed to be the same. So we can just consider a unit of one term. The first term, del itself, has unit of 1 over meter. Q, which is heat flux, supposed to be energy per unit time, which is watt per unit area. Of course, watt itself is joule per second. So I have 1 over meter here. Watt is joule per second, and joule is Newton meter. So I have Newton meter per square meter second. All right? This second appears from watt equal to joule per second, and expand this joule into Newton meter. All right? So if I combine this, I can get Newton per meter square, meter cube, and meter per second. All right? Consider unit only. You see that this term is force per unit volume. Okay, keep that in mind. We can have force per unit volume multiplied by meter per second, which is velocity. Why do I do that? Why did I do that? Let's move to this part. First two terms was done. The net flux was done, represented by this side of the board. The next part will be the rate of work by external force. If I rewrite it, work by external force. Okay, and I erase this for the moment. From chapter 9, we derive work as work itself equal to force time distance. Okay? In other words, W will be force, which is vector, dotted by vector representing distance. If you take differentiation, you get dotted dr. We did this already in chapter 9. Okay? This is just a repetition of what we already learned. Now, if we differentiate it with respect to time, then this on the left-hand side it would be rate of work. On the right-hand side, that would be differentiated with respect to time as well. And this vector of the distance differentiated with respect to time is basically velocity. So you end up with F dot V, just like what you got from chapter 9. Okay? If we check the unit, this would be Newton meter per second. All right? Now, in this case, for work by external force, our external force is basically gravity force. So if our force is gravity, that means F here is equal to mg, where m is mass and g is gravitational acceleration. Okay? We want to put this kind of term into the balance, but keep in mind that the whole equation for the balance has unit of force per unit volume. Now we have only force. So if I want force per unit volume, that would equal to mass per unit volume times g. And this mass over volume is density times g. And g is a vector. All right? So, understanding this and keep this plugged into this part, you see that the work by external force term here is supposed to be force dotted by velocity, and force itself is rho g. Note that is supposed to be force per unit volume. So this term is basically rho g dotted by v. In other words, I can say it's rho times v dot g. Okay? Rho is scalar, you can take rho out. And dot products can be swapped. So if I swap this, I get rho v dot g. Now, if we neglect energy production for the moment, there's a very rare case to have non-mechanical work like electricity into the system. If we just consider flux going in and out and work by external force, we can rewrite our energy balance. Okay? So our energy balance starts with net rate in plus work by external force equal to rate of energy accumulation. Okay? Net rate in is this term. So I copy everything here. All right? These four terms, 1, 2, 3, and 4, are net rate energy in, net rate of energy fluxes going in. Please note that right now I keep these two terms together. These two terms are kept together. This is flow work, and this is also molecular transport, work by molecular transport by shear stress. So they are some kind of the same thing, so I keep them together. Okay, you can say that these are basically flow work. And then work by external force, which is rho v dot g. So added by rho v dot g. Equal to rate of energy accumulation. Energy accumulation is basically change of energy with respect to time. And energy here is supposed to be energy within the system. It is consisted of kinetic energy, internal energy, and for the moment, I want to keep potential energy away for the moment. Okay, I will prove in a minute that potential energy is already there somewhere. Okay, so this part would be energy accumulated in the system. Now, if I define potential energy per unit mass in the same manner as internal energy per unit mass you had over here. If I say this one is phi with a hat itself represents per unit mass. Okay? Definition of this phi was done by G equal to minus del phi. How did we get this one? It's kind of complicated. It involves Newton's law of gravity. But in the plain, simple equation, let me show you this. In this part, I can say G, which is a vector, is basically minus del itself, del phi. Phi here is scalar. Del is differentiation with respect to position. So if I write this as a vector, del is I, which is unit vector in x direction. D by dx, the whole thing here is x component of del, right? Operated on scalar entity phi. So I get phi. This is x component. For y component, that would be j differentiated with respect to y, operated on the same scalar entity. And then z component in the same manner. All right? This is just the same equation from this vector notation. Now, if I take this z component and I said it is written by GC. GC is basically minus d phi by dz. All right? If I integrate move dz into the left-hand side and integrate the whole equation, on the right-hand side, I will get phi. On the left, of course, I swap this a bit. On the left, gravity is constant, and then you move z into the left-hand side and integrate it, you get z. Okay? So basically, this one is potential energy per unit mass equal to g times distance. We have familiar notation that potential energy is mgh. This is what you learned from high school. Potential energy is mass times gravity times height or distance. If I take mass here, I get potential energy per unit mass equal to GH, which is exactly the same as what we derive here. The only question is, why negative? Okay? So negative sign here was placed in here because imagine this. When you have gravity going down, let's say this is the Earth, gravity is going in the downward direction. At the floor, potential energy is low. Down here, I have low potential energy. Up here, potential energy is high. So high potential energy is up here. You can see that the direction of the increase in potential energy from low to high going against the direction of G. Therefore, the sign are totally opposite. I have to put minus over there. This is just signifying that the potential energy, the increase in potential energy is going against the direction of the G. All right? So if you repeat this calculation for X and Y component, you can get G in general. Okay? So if you accept that this definition is okay, then we can use it. Now, in our balance, the only term containing G is the external force or work by external force, rho V dot G. So if I calculate rho V dot G and using this notation, all right, I have minus from this part. Rho is scalar, so I can move rho together with the V. I get rho V dotted with del phi. Okay? And this dot product, you can expand it. There's a properties of dot products like this. If you have del dot of the scalar times vector, this is equal to del S dot V plus S del dot V. This, if you can imagine this just like what we have differentiation of the product. Differentiation of u times v equal to u dv plus v du. This is similar, but it's not the same. This is a vector notation. And we can see that it's somewhat the same, in the same form. If I said my S is phi is scalar, S is scalar, and my V here is rho V. So I can write del dot phi rho V. Of course, I combine rho V together. Then on the right hand side, I will get del phi dot rho V and plus phi del dot rho V. Okay? And this term, since it is dot product, A dot B is equal to B dot A. You can swap these two parts and you end up with this one. Basically the same thing. So I can write this part as this subtracted by that. Okay? So eventually I get minus del dot rho V phi, which is this term. I can move phi inside as well because phi is scalar. No, I'm sorry. This is this term, okay? And this term plus moving this term to the left-hand side, you get minus, and you get minus from here, so it's turned into plus. All right? Now, the whole term here, earlier I wrote down this equation, d rho by dt equal to minus del dot rho v, which is equation of continuity. Okay, this is equation of overall mass balance, and you can see that this term and that term are essentially the same. So you can say that this part, the highlight part, is basically minus d rho by dt according to equation of continuity. All right, so let me erase this. And continue on this side. All right, if I write this term first, I get minus, and I can move this scalar inside differentiation. Okay? If we assume that this gravitational field or potential energy per unit mass is not function of time. So if it is not function of time, I can move it inside the differentiation with respect to time. Or you can move it out, doesn't matter. Okay? So if I move it in, I get rho phi for this term. And that term, I repeat it, del dot rho v phi. Now I can replace it in here. So if I copy, all right. Let me erase this to get more space. Okay, so just repeat it again. On the left hand side, this term is flux. Flux going in, net flux. This is work by external force or by gravity, which can be translated into potential energy term. On the right-hand side, this is accumulation of energy in the system. And if you look at the equation, you see that this part is differentiation with respect to time in the same manner as what we have on the right-hand side. So if I move to the right-hand side, this turns to be plus on the right-hand side, and then I can add potential energy to this term. So if I write that first, I get d by dt okay. Then this part, you see that I have del dot, I have v in the same manner as this term. Okay, rho and phi is scalar. So I can rearrange this a bit to be minus del dot rho phi times v. Okay, and move this whole term here to join this term. Doing so, I get this Q unchanged, and then this term, I have kinetic energy, internal energy, and potential energy added. All right? And this work term, flow work term, remains the same. Okay? So if you look at this equation, the final equation, you see that this seems to be accumulation because it is differential with respect to time. So this is the change of total energy within the system, and this energy can be divided into three parts: kinetic energy, internal energy, and potential energy accumulated into the system, just like what we learned in thermodynamics, equal to whatever transfer into the system by means of conduction, convection, and convection follows the mass. You put mass into the system, mass carries energy. There are three kinds of energy being carried: kinetic energy, internal energy, and potential energy was carried into the system and added by flow work. So this is the whole equation in familiar form, that energy can be split into three terms, into three forms, actually: internal, kinetic, and potential. Okay? So by doing this, I just want to prove that you can derive the equation into the form that you are familiar with in thermodynamics. But the form of equation that we are using mostly, we would prefer the equation in form of internal energy and internal energy and kinetic energy. We do not prefer the potential energy. All right? Now let me rewrite the equation that we prefer. All right, this is the form that we prefer. If you compare between these two equations, it looks familiar. It looks similar, actually. The difference is basically on the left-hand side, the form that we prefer has gravity. The right-hand side is represented by potential energy instead. But in transport phenomena, gravity was used so many times, especially in momentum part, so that's why we prefer this form. Okay? Now, I want to keep this for the moment and start with a new topic. This topic is basically on chapter 3. Chapter 3 is still in momentum. We skipped this part because it was not relevant during that time, but now it will be relevant. So I would go back to chapter 3 a little bit. In chapter 3, we have equation of motion, which looks like this. Okay, this is equation of motion. And you see that this is momentum. Equation of motion represents momentum balance. So this is momentum change with respect to time within the system. So it is accumulation of momentum within the system. This is minus del dot, as I said, minus del dot something that will be net flux. This is net flux by means of bulk flow or convective transport. This is net flux minus del dot tau. This is net flux of momentum flux by means of molecular transport. And molecular transport of momentum contains two terms, either tau and pressure. Okay? And then external force, gravity force that create momentum. So this is basically rate of flux going in and out. This is net rate of flux going in and out, plus generation of momentum by means of external force. So, if I take this equation and then do the mathematical manipulation by taking a dot product with velocity. Why do I do that? So let's take the first term, okay? d by dt of rho v. If I take this term and dot it with velocity, what would happen? If I write it down, expand this into vector form, the dot product I can swap. I can take v dot by this term. If I do that, the first component in the dot product, you take each component, multiply by each other, and then add them up. The first component is vx. Multiply by the first component of this vector, which is del by dt rho vx. Right? This is vector, x component of this is vx. Second component, that would be vy, d rho vy by dt. And then z component. All right? Now, earlier, if I take vector v and find the magnitude, I can get v squared equal to vx squared plus vy squared plus vz squared. This is the way to calculate magnitude of the vector from its component. So from here, if I take 1 over 2 rho v squared, basically I take 1 over 2 rho multiplied by everything on the right hand side. And then if I differentiate with respect to t, on the right hand side, I get differentiation with respect to time. Inside, that would be 1/2 rho vx squared, vy squared, and vz squared. Right? If I take one component here, this first component, just consider this component. Let me write it down here. 1 over 2 rho vx squared. If I differentiate it, of course, 1 over 2 can go out. If density of the system, if density of the liquid is constant, I can take rho out. Okay? And inside here is differentiation of vx squared. You get 2vx dvx by dt. All right? These two and these two cancel out. And then I can move rho back into differentiation again if rho is constant. So I end up with vx dvx by dt. Okay? Oh, rho as well. Rho vx by dt. And you see that this term and this term are exactly the same. They are exactly the same. So I can say that this part is basically d by dt of 1 over 2 rho vx squared. Of course, the second part will be the same thing except this one changed into vy, and then this one will be vz. Okay? So in that case, if I repeat this, this would be d by dt 1 over 2 rho vy squared. And this would be d by dt 1 over 2 rho vz squared. All right? Add them up. Please note that Vx, Vy, Vz are all scalar. Okay? So if I combine these two terms together, I end up with d by dt of 1 over 2 rho v squared. Okay? Why do I do that? Because 1 over 2 rho v squared here is kinetic energy per unit volume. No, kinetic energy per unit mass that we use in equation of energy. All right? This term is exactly the same as this term. Okay? And keep in mind again, what are we doing now? So let's step back a bit. We start from equation of motion, which is equation for momentum balance, and play some mathematical trick with this equation that if you take accumulation term here dotted by V, you end up with the change in kinetic energy with respect to time. So that means if somehow I dot velocity through the whole equation of motion, you end up with accumulation term associated with kinetic energy and flux associated with kinetic energy, as well as the external force to create kinetic energy. Okay? If you do that, I do not want to go into the detail, but the concept is just take V dotted everything and rearrange mathematically. You will end up with d by dt. I show you the left-hand side, this part already. All right? Everything on this board, on the right-hand side board, is here. Then, for the rest, you can do it by yourself, or you can just simply trust me. You get this part. All right. Now, if you go back to this momentum balance equation a little bit and try to imagine you dot it with velocity. The first term, when you dot it with velocity, you add another velocity. So that's why you have 3 velocity here. The second term here, if you dot it by velocity, it seems to be like a dot of the whole thing. You can split into the dot of the products. You end up with 2 terms. The third term is a dot of del dot tensor, which is complicated, and you end up with something weird here. This is called double dot. One single dot, you reduce the direction of 2 vectors. Vector with one direction, you reduce into scalar. Okay? But for double dots, that means you originally have tensor which has 2 directions. After double dot, it turns into scalar. All right, but we do not use this part that much. So just bear with me on this part. The last one is rho g dotted by v. You end up with this one. All right. So you have 2 equations. The first equation on top is basically equation containing kinetic energy and internal energy. Okay, this one is kinetic energy, or EK. This one is internal energy. On the second equation, you end up with EK only. All right? Now, what do we do? If this is called equation 1, and this is called equation 2, taking equation 1 subtracted by equation 2, what do we get? Just look at the accumulation term. It would be easier. You have kinetic and internal subtracted by kinetics. So you end up with internal energy change, right? So basically, equation 1 is overall energy. Equation 2 is kinetic energy only. So when you subtract kinetic energy only from overall energy, you end up with equation representing internal energy. So just like this, you have overall energy, or overall energy balance. If the temperature change in the system is dominating, that means your system have change in internal energy more significantly than the change in kinetic energy. So in that case, if U is dominating, you can ignore kinetic energy. Okay, this route here is usually the common route that you took in thermodynamics. Whenever you have system changing in temperature, internal energy change is dominating over kinetic energy change. You can ignore this part. You can ignore kinetic energy part. On the other hand, if kinetic energy change is dominating, you can ignore internal energy part. Okay, this part was considered in unit operation 1 when you consider flow of fluid in isothermal condition. If there's no change in temperature, no change in phase, internal energy of the whole system does not change very much. But when you change, like you put the pump into the flow, velocity change, kinetic energy is dominating, you take this route. Okay, so on one hand, you have overall energy balance that you learn in principle of calculation in chemical engineering. It would be easier to ignore one term, ignore kinetic energy, if U is dominating. This one you took in thermodynamics. Normally, thermodynamics ignore this kinetic energy or mechanical energy terms. On the other hand, if the system is isothermal, you can ignore internal energy and consider kinetic energy only. And this equation turned to be familiar equation called Bernoulli equation that you use in unit operation 1 or in fluid flow. Now, equation 1 on this board is overall energy. If I subtract this kinetic energy, if I subtract kinetic energy out, what I have left would be equation that somehow represent internal energy. It would be this route. I ignore kinetic energy or subtract it out. So the equation should represent internal energy only. Of course, there will be potential energy as well, but let's ignore that because we know potential energy is embedded in gravity. This gravity would cancel out anyway. So the result from equation 1 subtracted by equation 2 would be equation representing change in internal energy of the whole system. This equation will be useful whenever we can ignore kinetic energy. In other words, whenever that your temperature has changed. Okay? And in this session of energy transport, energy or temperature of the system always change. So therefore, it's always dominating. This equation will be very useful later on. So let's erase this. Now taking equation 1 subtracted by equation 2, on the left-hand side, I get d by dt. Taking kinetic energy out, What I have left should be internal energy only. So this is internal energy change with respect to time, equal to, the first term here remains the same, minus del dot Q. All right? Second term, if you notice, this part and that part are essentially the same. So this and that should cancel out. What we have left is del dot rho u. Times V outside. Okay? And you see that this term and that term are essentially the same. They cancel out. What we have left is this term. And we have minus here, another minus over there, so it's plus, but you take this minus, the third minus, making the term to be minus. All right? So this term must be kept. This term is left. This term is left. This term is left. Then you see this term and that term are essentially the same. They will cancel out. And this term and that term would cancel out, leaving only the weird double dot term. So the last term would be minus here, because we have minus, another minus, and the third minus from here, end up with minus tau double dot del V. All right? So the whole equation here is basically equation representing energy change in the system, assuming that kinetic energy is not important, potential energy is not important, so it is applicable for system having dominating internal energy or system having temperature change. This is called equation of internal energy. Now, but internal energy itself is not very useful because we cannot measure internal energy. In order to make it useful, we want to change to enthalpy. Again, enthalpy is not measurable. We want to change enthalpy into temperature and pressure. Doing that can be done using thermodynamics, right? Like this, U equal to H plus P over rho. You can convert this U into enthalpy. And then using thermodynamics, like dH equal to Cp dt plus V minus T dV by dt P dP, and so on. All right? If you plug this into that and plug that into here, you can change this equation into something measurable. On the left-hand side, you end up with rho Cp dt by d term. Now, this capital D is substantial derivative. We learned this in chapter 3. It contains del dot V. Okay? Then, the first term remains the same. This term will be changed accordingly. We change U into H, change H into T and P. I do not want to go into the detail. As a result, you get this part. All right? This would be the equation that we are going to use frequently in chapter 11. But it is rather complicated, and in general, you can say this one is related to Cp, and there's a velocity hiding inside. So this term is about convection. This term is definitely conduction. These two terms are somewhat relating to work, okay? But if we consider special circumstance, we can reduce this complication a little bit. So special case would be a fluid with constant density. Okay? If fluid has constant density, density appears here. This is change in logarithm of density. As long as density is constant, differentiation here turns to be 0. So you can drop the whole term here if your fluid is incompressible. All right? So under this assumption, you end up with this equation. Okay? And then I can use Fourier law to replace this flux, conduction flux, by Fourier law equal to minus k del t. So you have minus and minus, del dot del, that turns to be del square, which is Laplacian, k del square t. Plus, in this case, if I use Newton's law, that means I will assume constant viscosity in addition to the first assumption that density is constant. If I use Newton's law, I can replace the whole term here into something a little bit simpler. You get constant viscosity times what we call here is dissipation function. This would be an equation that we will use for examples. All right? You understand that this term will be convection, this term will be conduction. This term, however, what is it? It is called dissipation function, but in physical meanings is related to viscosity. So therefore, this term is directly related to what we call viscous heat. Okay? So any kind of system having very low velocity or not so fast velocity or low viscosity, you can simply drop this term and then you end up with simple equation. So this is for the derivation of equation. This is equation that we want to introduce. The rest is just an application of this equation. I will show you in the examples next time. All right?